like that. All right, so we're recording now. Pattern recognition. Pattern recognition is the first one of the components of problem solving and computational thinking that we're going to break out and try and look at today. We're going to look at this today. We're going to look at these other three at a different time. So let's look at pattern recognition. Pattern recognition, sorry, we remember this graphic here. Maybe I need to make this a little bit smaller so it fits on the screen. There's a pattern. And we recognize the pattern. And because we recognize the pattern, what we can do is we can create a module to solve just this. And then every time we see where this pattern would arise, we can implement our module, which solves just this. So we don't have to keep doing the same thing over and over again. We're not reinventing the wheel. So we invent the wheel once, and every time we need a wheel, we put a wheel. That's what we mean, right? So that's what we're seeing. And so as it says, it's one of the pillars. The other pillars are abstraction, represented there, decomposition, and algorithms. So a pattern, when you're in primary school, and even now, you probably were presented with lots of patterns like this. We see a series of numbers. There's some relationship between these numbers. What we typically do is we try and see a relationship between a number and the number before it. And if we can see that relationship, we can build up the pattern. So for example, what's the relationship between 6 and 2? The relationship between 10 and 6, and you see the relationship already. This, which is +4. So if we take this one, we get to the next one by adding 4 to it. Okay. Likewise, we tend to see in this one, we see a relationship. It's not going to work by adding. We're going to have to do something else. Multiply the number by 3, and we get the next number. The next one, we have a pattern which is slightly more complex. And this pattern was described by a fellow by the name of Fibonacci. So it's called a Fibonacci series. So just Google that name if you're interested in looking at that. And there's computer programs written for it. Fibonacci. Nazi with a, not like N-A-Z-I, N-A-C-I, because it's a Nazi, I guess it's an Italian name. 1 and 1. This is the way this one works. This one we have to use two things together. 1 and 1, if you add them together, what do you get? 2. 1 and 2, you add them together, what do you get? 3. 2 and 3, you add them together, what do you get? 5. 3 and 5, 8. What's the next one? 13. So you know the pattern. So that one is a pattern, which is the Fibonacci series. You take 2 numbers and add them up. Here's another pattern. Remember these guys? The Jacquard dude? Jacquard from 200 years ago. He came up with this thing with what do you call them? Plates of wood? I don't know, slabs. They're very thin, veneers of wood, I guess you'd say, and they got holes in them. And the holes, you can put a pin through it, a rod, and that will determine which string comes down in your loom. And so from that, you can get a pattern. Can people make a pattern like this? Sure, they can. They've been doing it in Iran and Turkey forever, right? And probably Egypt and other places as well. We do these kind of things. People have been doing it for a long time. But when they do it, a person does it. Actually, we pay more for that. We like that because we can see that it's done by a person. It's not perfect. And we can see their personality in it a bit, I suppose you'd say, right? Whereas we can make with a computer, there's no personality there, but we get an exact representation every time. And more important, it does very, very fast. Very, very fast means cheap. Cheap means everybody can have it. Relatively cheap. I mean, it's time is money, right? If you have to pay somebody to make that by hand, they're going to make it beautiful, but it's going to cost money. People's time, they need to have money because they need to eat. They need to have a house and they need to feed their kids. So you need to give them money. Whereas a computer doesn't need to eat, right? It doesn't need to feed its family. And it can work 24 hours a day. And so it's cheap. The handmade one is expensive because that guy who made it, he has to eat. If he's not going to do it if he doesn't make enough money to eat, right? And so it's going to be more expensive. All right, here's another pattern. This is a pattern that you will have seen before. Every time you buy something, every time you sell something, we put things into a receipt or an invoice. And the thing about the invoice is once you recognize the invoice, you know exactly where to look to find what information you want. You want to know the total price, look here. You want to know the discount, you look there, right? You want to know how many items you bought, look there. You want to know the name of the item, you look there. And the pattern is reproduced. If you're buying the same thing, if you're buying from the same company over and over again, you're going to do this so fast, right? You just look at the invoice, you know exactly what to look for. If you work in that company, everybody in that company knows exactly what is on that invoice and where. So it's a pattern, right? It's a pattern. It's a type of thing that could be easily written into a computer program, and it is, right? You go to Carrefour. Nowadays, Carrefour always asks me, do you want us to just email you the receipt? I'm like, yeah, save some paper. So I get an email. It's better, right? I got a permanent record and I don't have to throw away some paper. I know that was something funny, but I didn't actually pick it up, Omar. What? What? Sorry, no, honestly, I didn't hear it. I'm an old guy. I can't hear everything. Pattern recognition. Yeah, what? Some more stuff about it. Oh yeah, the idea here is we can see patterns that apply to many different systems. Okay, so the same kind of pattern is found in this system, and that system, and that system. So that's what we mean across problems. We've got an example coming up on that where we calculate the average. We calculate the average for a sportsman. We calculate the average for a weatherman. Still calculated the average. We've got another one is where we have one particular system and different components within that system are using the same pattern. And so let's look at those. Blah, 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 and blah. Automatically notice I'm just going to go on to this one. So here's those two different situations. So imagine the sportsman, he's throwing the disc, wants to know what is his average distance. Just going to add up the distances, divide by the number of throws, there's his average. You got the weatherman, also known as a meteorologist, wants to know the average temperature. Just going to add up all the temperatures, divide it by the number of times he had the temperature, and there's his average. So that could work that way. Now, that is a pattern across problems. Let's look at the pattern inside a problem. You got a company, they have customers, they have employees, they have managers, and we need to have a profile for every one of those people. So what are we going to do? The profiles are going to be different, but there's some pattern recognition. There's some things about them that are the same. Everybody has a name, everybody has an ID or something like that. All of that information will have to be captured. We do that in a profile capturing app, and that's going to be the same app that we use for everybody, just the inputs will be different. Here's another problem. The problem is to draw a shape. Got lots of different shapes, but we could use a single module to solve this problem. So the single module could take inputs of what is the length of a side, what is the angle of a corner. Triangles are all the angles. When we add them all up, it's going to be 180 degrees, right? So as long as our angles add up to 180 degrees, then we can have a triangle. As long as our lengths the length must be proportional to the angle that it's opposite, right? Remember that kind of stuff? And anyway, so as long as those sort of requirements are met, we can draw our triangle. Likewise, we could draw a rectangle knowing the length and knowing the angles. And likewise, these other things. And then we could have the color. So we could have a module that would do that. We could call that module an object. That's if we were doing object-oriented programming. So that's why I got the notes at the bottom there. Object-oriented programming uses this idea where we would create an object. The object would be a thing that we call shape. And then we would have some attributes that are related to that shape, which would be the length of the sides and the angles and how they're related to each other. Then we could draw it. You will learn object-oriented programming soon because you have to do programming in Python. We start programming in Python at this course, but it won't be object-oriented. So don't worry about that. Neither you'll do Python in 1201. That's also not object-oriented, but when you get to the class after that, you will be doing object-oriented, where you'll have to create classes and you'll have to create modules. It'll be fun. All right, so we're using some object-oriented programming here. And what we do is we have an object that we're going to call a circle. And so the circle has some attributes about it. So for example, a circle has a radius or a diameter. Diameter is just 2 times the radius. So they're very tightly related. A circle is going to have a position. It's going to have a border, a circumference, right? We can have these things which are half circles or other proportions of a circle. So here we refer to a cut, but we could refer to an arc, which is the number of degrees out of 360 that we're going to draw that. The border of a circle could be solid. There could be also some fill in the circle. All right. So just using circles, we could draw this picture, right? All it is circles, except this is a half a circle. The other attribute about that circle, I guess, is the center. What are the coordinates of the center? What is the position from which that circle is drawn? Okay, so here's some other problems that have been broken down and patterns have been recognized. Do you recognize a pattern there of a rectangle repeated multiple times, right? Rectangle, rectangle, rectangle. You see a pattern there of a circle, circle, circle. It's a bunch of circles. It's a bunch of green circles that are sitting on top of each other. Hey, Chicky, yeah, look at that one, eh? And do you see a triangle? Any more? Yeah, the corona of the sun. Oh, corona. Why did I say that word? The corona of the sun is made up of yellow triangles. It's a Chinese sun. Oh, that was a bad joke. I'm sorry. All right, so we're back to this. So back in the way of thinking of object-oriented language, then we have these objects. So I got an object of a rectangle, a circle, and a triangle. They have some attributes. If we input some data here, we can create a rectangle of a certain width, height, border, fill. We can do that. Likewise for the circle, likewise for the triangle. And now the triangle, there's one extra thing down there that's sort of hidden that I'll bring up. Yeah, border fill. What is the who? So we've got a rotate because these triangles are all oriented differently. So I think that's what they mean by the rotate. Next one is nice because it's food. I have to say, I'm not really relating to this, but, I don't really cook cakes. But apparently there's a pattern there. And I see an anomaly in the pattern because the pattern is not exactly one-to-one pattern because we got to preheat. I would say that this is all sort of mixing, but then we have the baking here, and then we got some whisk. So this depends on, do we put the cream on? Cream is different, right? We do it afterwards. That's why we got these arrows. Let's ask the robot. Okay. Now get to the good fun stuff. The subroutine. Draw a circle. We could have a subroutine draw a circle. This could be a module in an object-oriented language, a class. So in this class, what we do is we give it a bunch of parameter inputs. Now, last year in the quizzes, we had a question which is, the input to a routine is called an argument or a parameter. Both of those are true. Okay, argument is just another name for the parameter. Okay, so I'll check that if it comes up again. I mark both of those right because in your notes you'll see and in the textbook it says they're both the same thing. These are arguments or these are parameters. Parameters is probably the word you're going to see. All right, so those are inputs. Depending on that, we get a different circle, right? Yellow. Let's go, man. I'm going to be tired when I finish this. Okay, subroutine. Now, the thing about a subroutine is we noticed in that smiley face, there was lots of circles. So we draw a subroutine, which is a draw circle subroutine. And all we have to do is put the different things in. We can use the subroutine over and over again. We don't have to reinvent the circle, reinvent the wheel. Hey, it's just like that, isn't it? We don't reinvent the world. We only have to make the subroutine that does the wheel once. The idea of working backwards is about the goal. The goal is the ideal situation. That's where we want to be, right? That's what we want. That's the goal. Once we know where we want to be, we can decide what's the difference between where we are now and where we want to be. And then we can say, oh, well, what would it be like if we were almost where we want to be? And we can work backwards from that. You know, maybe we're 90% to where we want to be, and then we were 80%. You know, I want to be in the Pearl. What would it be like if I got to Katara? You know, you get the idea, right? And then what would it be like if, you know, eventually I get to the Pearl, but I get there one step at a time. I don't need to go to Katara to get from here. Yeah, going to Katara would get me towards the Pearl. Okay, we're almost done. This is our robot that's running over people, right? The self-driving car. Maybe the self-driving car won't run over the person as long as the person looks at the self-driving car like that so it can see the eyes. Sorry. But if you had a bunch of cats, maybe a computer could tell that this is a cat. Now, how it would know it's a cat? It would, by the face. The distance between the eyes and the nose and the mouth is different in a cat than it is in a person, right? So a computer could tell the difference between a cat and a person, probably. Now, how that would happen is we would kind of call that artificial intelligence. We train the computer. We give it a training set. We give it like 100,000 pictures of cats. And it measures all the eye distances and all the nose distances, stuff like that. And after all of that, it's able to sort of say, okay, the average distance between the eyes of a cat is this. And so does this thing fit in that, in a range that is true for a cat? Like this?
Yeah, but there's like this picture of dogs that look like fried chicken. No, really, I don't know. There's a photo of dogs, like golden retrievers that look like fried chicken. Fried chicken? Yeah, the KFC. This lady's hungry. No, but I can't. If I find the photo, I'll send it in the club. But it's like a popular meme.
This is a joke that we have that I like. I like to how you call it, trolling people on the internet. If they show a picture of like a snake or something like that, and I want to make a mean comment, I'll say tastes like chicken. Now, one of my friends, you know, I'm so want to do this so bad, but I can't, you know, because she's been my friend for like 50 years. But she got a bunny, and bunnies actually do taste like chicken. I want to put there, but I haven't. I'm resisting that temptation. Like every time, oh, what is it? He tastes like chicken. She's like, I love my bunny. I love my bunny. Yeah, but it tastes like chicken. I know, because you know what? When I was like 11 years old, I was in primary school. It's show and tell, you know. We used to have show and tell. So you bring something from home. Oh man, we had some weird things come. One guy came in with a skull one day. Show and tell, right? I mean, it's got fillings. I'm like, geez, man, maybe we should be calling the Royal Mounted Police. Skull. But anyways, oh yeah, the fried chicken dogs. That's bad. Anyways, one day the kid brought in his bunny, a big rabbit. It's like, oh yeah, that's nice. 2 days later, he brought in the meat. He said, that's the bunny. And every one of us ate it, and that's how I know it tastes like chicken. A true story. What? No, we're all okay. I mean, this is like 1960. We eat everything back in those days. I lived on a farm. We have lots of animals. We kill the animal, we eat it. You know, it's just like that. Nobody cared. Back in the day, right? We didn't have pets. We didn't have pets. We had food that walked around. That's why we have Corona. All right. So, well, some food flies around. Okay, so can a computer recognize a person? Well, apparently the computer can recognize this. Your computer, can it recognize? So there's a difference. Can it recognize a person, or can it recognize a person, as in a particular person. Yes, so yeah, this computer is recognizing that these are people. And, same way it recognizes that this is a cat. But this computer is recognizing a person, and it's recognizing you. So that's kind of a little bit different. That's facial recognition. That's what you got on here, right? So on here, I got kinds of security, so I can put my fingerprint on there and I can open it, or I can use a code. Or if I'm really lazy, I can just point it at there and, oh yeah, I recognize that's you. Right, so it does facial recognition, right? So how it's doing that is because, all right, all humans, their eyes, the distance between their eyes falls within a certain range. It's different than a cat. All humans, the size of their nose falls within a certain range. It's different than cats. But every human is slightly different. Every human is slightly different. And so if we get the exact measurements, as opposed to using the averages, here we're using the average, right? So on average, this face is different than on average that face. But we're not using averages here, we're using exacts, right? This person, exactly, their eyes are that far apart. And that is different than that person or that person or that person. So this person, they can show their face to the phone and the phone will open up. But those other people, even though their eyes and nose, etc., fall within the average, they don't exactly match. And so they're not going to recognize it. Does that make sense? So isn't that fun? I enjoyed that. I don't know if you enjoyed that. All right, so we got some questions that go with this. Computational thinking. We've got 4 different areas of computational thinking that we're going to talk about in this course. Decomposition, pattern recognition, which we talked about today, abstraction, and algorithms. Now I've got some questions for you. This could be like a multi-choice question. I don't know if it's going to come up in the quiz, but it won't be in the quiz that you're having on this week because this is today's stuff, maybe after this. All right, so what's computational thinking? Only one of these is the best answer. Did you say B?
I said C.
Thank God.
I said
Alhamdulillah. That's it, right. So yeah, is it that? Set of techniques, approaches help solve problems?
I'm saying giving instructions to a computer to think like a human. Perfect.
That's a good answer. It's not a bad answer, but the best answer is this, because computational thinking doesn't have to involve a computer. You can do computational thinking to solve other problems, like how am I going to make this dress? Anybody make dresses nowadays? See how old I was? When I was a kid, my mom used to make dresses. Yeah. My mom used to make shirts. My mom used to make shirts that I used to wear. So that back in the day, right? We used to do all kinds of stuff. Do we need to think computationally to help us program? That's kind of the same question that we had just a minute ago, right? Solve complex problems more easily. Which one? B. I like that answer. Who said B? You guys are good. I'm liking that. All right, so B, let's go back to see what's B because somebody that wasn't watching. Solve complex problems more easily. Could be with a computer or maybe not. All right, so which is what? What? You guys said coding, which is C. I like that answer because this one is about not. Computational thinking doesn't. We had 4 areas, didn't we? Right? Decomposition. What was the other one? Algorithm, abstract, and pattern recognition. Good. Not coding.
all of these questions are going to be on the quiz.
None of these questions are going to be on the quiz because the quiz is about weeks 1 and 2.
But it's going to be like this, right?
Maybe. I don't know. Usually the multi-choice questions on D2L have like 4 questions. Yeah, anyways. 4 choices. Which of the following is an example of thinking computationally? Planning your route? Yeah, it's too easy, right? Do you remember what was in the lecture, right? Yeah.
So what's the answer?
So if you're asking somebody else to plan, that is not computational. If you're wandering around randomly, that's not computational, right? Random is not computational. Asking somebody else is not computational. Planning, that was a nice word for computational, right? Plan. Maybe we'll see that again. Oh, Oh, yeah, I mean, there we go. That's way too easy, right? They keep on using that word. So this one again is, which one is not? It's the one that doesn't have planning in it, right? Not to say that computational thinking is just about planning, but planning is part of computational thinking. Oh, by the way, you guys like planning? If you like planning, maybe you like to be a project manager. There's a course in our degree about project managing. You can make a lot of money, man. This is where the money is. So, you know, the programming is a little bit of money. The planning there is where the money is. I mean, do it. All right, so yeah, you need to be able to do that too. You've got the exact right personality for that. So yeah, do it. Yeah, that's where the money is. Do it. I'm wrong again. That's like the 5th time this lesson. Apparently. Which of the following is not example? Did we do this one? Bossy, we don't know anybody who's bossy. All right, so the bossiest friend should decide us where to go. Is that true? Is that computational?
That's clever. Don't do any work.
Is that computational thinking? No, that's psychological thinking. That's like, do I want to have a confrontation or not? No, I don't. So the bossy person will get their way, right? Or yes, I do. So we're going to have the confrontation. Considering the different options. Oh, okay. Okay, so I'm liking that answer better. Okay. Yeah, C is kind of relates to what we did in class. Discussing. How much time? There we go. It was in the lecture. Oh, yeah, it's the not. That's right. These two we liked. Thank you, Aisha, for pointing that out. Not A. Very good. All right. What is complex? Now, in this one, we have to go with best answer. Because I think when I looked at this one, none of these I didn't like.
I'm going with B.
I would say C, because in order for it to be complex, you don't,
No, I'm going with B because.
Yeah, B, because if you understand.
Yeah, if you don't, exactly. Like,
No, it says,
if
what
you can
is
understand
A?
it, you can
A
solve it.
complex problem
But
is
if
what
you
you
don't
understand.
understand it, you can never solve it.
I'm saying it's C because if you can't understand or solve it, then it's definitely
Yeah,
C. There's no point because you can't solve it even if you do understand.
Look, if you can't, if you understand it,
You
you can still
understand
solve it.
Okay, so there's a bit of ambiguity there. We got a bit of argument between solve and understand.
You can't solve it without understanding it, but you can solve it with understanding.
Yeah, if you can't do both, then it's complex.
You can't solve it without understanding it, but you might be able to understand it without solving it.
It's B.
It's B.
I think B is best.
Yeah.
Thank you. Which computational thinking technique involves breaking a problem down into smaller parts? This one we won't have a controversy. It's only one answer, right? Smaller parts is A. Decomp. To create a successful computer program, how many computational thinkings do you need? Okay, so what I want to say here is yes, the answer is 4, according to our model. Our model is a simplification of the real world. Could somebody else have another model? Yes, and their model might have 5 things in it, or it might have 6, or it might have 8. The one we got is 4. It's not the real world. It's just a model that we can use on the real world that just happens to work. We like this model, so we use it. Okay, so to be pedantic, we're going to say it's 4. But next year it might be 5 because, I don't know, because Aisha comes up with a better model, right? The genius comes up with a better model. That's right. All right. When is a computer most likely to be used when using computational thinking? Are we going to use a computer for decomposition? Look, never say never. I mean, maybe. All right. Are we going to use a computer for programming? Well, yeah, it's kind of hard to program without a computer. So, I mean, I'm going with a really, really, really maybe. That's a big one. Yeah, I'm going with that. Writing algorithms? Maybe, but nah. Yeah, the answer is B. Thank you. We're done. Okay, so if you have any questions, just